they should give you justification for why the statement is true. Okay. So let's look at the theorem. 1.3.9. So suppose we have set S and T with S as a subset of T, or A of the theorem. So if S, T is a subset of S. So if S is countable, then T is countable. Okay. So this should make sense. The actual technical proof is rather detailed, right? But it should make sense, right? If the superset is countable, then how would that be uncountable, right? Every element in T is contained in S, so if it was uncountable, then you would get some type of contradiction, right? So I guess like we can like kind of talk about the proof sketch. So this is a proof idea maybe. So if T is finite, if S is finite, then clearly T must be finite. And if you look to the definition of being countable, it said it's countable if it is finite or enumerable. So in the case that S is finite, which means that's it, one of the possibilities of being countable, then T must be finite, which means it's also countable. So we can assume that S is infinite, otherwise it's already done. So we may assume S is infinite. Okay. So we're assuming that S is countable, so it's either finite or infinite. In the case that it's finite, we're done, so we're going to assume that it's infinite. Infinite and countable, so it's enumerable. So maybe the idea would be something like by contradiction, or maybe we don't even need contradiction. Let's see. So yeah, we don't need contradiction actually. So we're assuming that S is enumerable, so let P naturals to S be bijection. Something like that, right? So then we can, so in particular, every element in T, right, is an element in S. So since this is a bijection, the elements in T, right, have pre-images over here in the naturalist, according to this function. So how can we like kind of informally write this? So let maybe, and again, this is, I'm just kind of like winging it right now. I didn't really think about proving this before lecture. It's important to note this there. So now I'm just kind of working my way through, which is, I think, good for you to see as students, that you understand the process of building a proof when you have no idea where to go. So my first instinct here is to say let that X, which is a subset of the naturals, where phi of X equals T, or something like that. So we know, so just know that phi of the naturals, that's equal to X, right? So we know that T is a subset of the image of the naturals under this function, right? So in that case, we know there's some subset of naturals that's going to equal that. Every element in there has a pre-image here because this is a bijection. So the idea here is that if we restrict the domain, so like maybe we can draw a picture here. So this is like the naturals. And here's S, and we know that this function B was over here. Okay. Right? And we know that everything over here has a pre-image over here. So like maybe here's T. So I'm just saying X is over here, and everything in X gets mapped to T. So there is a one-to-one correspondence between T and X. Okay. So again, this is more or less an idea behind it. It's not actually just trying to get you to think about how you would go about doing it, right? I suppose in a separate video, I'll post the actual formal proof, and you'll see that it is kind of detailed and a little bit long, but I'll post a second video for that. So more or less, this is the thing that we observe here. Right? But now we've kind of got ourselves into a situation here, because if T is so now we have that this is a subset of the naturals. So X is a subset of the naturals, and it's in one-to-one correspondence to T. But how do we know a subset of the naturals is denumerable? Like if that set's denumerable, then this would be true. But that's like, we're like back here at our plane. Like if S is countable, then T is countable. So we're stuck, right? So this wouldn't be a way to prove it, in other words. So maybe we can think of a different way. Let's say, thinking. And I hope that you're thinking with me. I know that there's a bijection. I can at least say that. Okay. And I know that there's a bijection because I'm assuming that S is countable and it's numerable. So it's an infinite set that has a bijection with it. So I know that. And I know that intuitively, I know that if I restrict, so every image in T has a pre-image over here in the naturals. Right? Every element in S has a pre-image in the naturals according to that function. So in particular, I know if this is a one-to-one non-two function, it's a bijection, I know that it has an inverse. So now I'm starting to think about inverses. So for each, so I'm going to say let that be the inverse function. Okay. And for each, maybe I'll say x and t that this x, which is a natural number, is the pre-image of x. Okay, so that's a natural number. So we know that each of the elements in S has a pre-image that's a natural number, a unique pre-image, right? So this is unique. Unique. It's a unique number. So that set X actually I can define as the pre-image of T. That's a better way to define it. Okay. Okay. So what can we say now? So this implies what? So X is just a collection of numbers, right? A collection of numbers. Okay. So then it's tricky, right? It's a little tricky. Again, I'm trying to form a bijection between the naturals and T. So, oh, wait a minute. Wait a minute. So, if T was uncountable, so if T was uncountable, right? Then, since this is a one-to-one correspondence between elements in T and the pre-images here, and these are just numbers, then X is uncountable. Right? If we just reverse back from T to X, this is the inverse. So that set of natural numbers is uncountable. Right? And we're assuming that T is infinite. If it's finite, then we're done. So we're assuming that T is infinite, uncountable. So then, if T was uncountable, then the inverse image, the pre-image under this function, which is a bijection, that must be uncountable because there's a one-to-one correspondence between those two things. So then we have the naturals, and some subset of the naturals we call X as being uncountable. So I'm looking at that set X and saying, is that uncountable? Like we know it's not, right? We know that that set X is not countable, is countable, but if we assume that T is uncountable, then that must be uncountable. uncountable, and infinite. So what can we say now? We can say that, so these are just elements in the naturals, right? So the naturals have orderings to them. So X is just some subset of that ordering. So what I'm going to do now is say something like X1, X2, X3. I can just order the elements in X increasing size. Like X1 is the smallest number in X. All right. So I think I know how to prove it. So let's do this. So again, have this definition down. Okay, so we're assuming by contradiction that T is uncountable. Since we know this function here is a bijection, or the inverse of the bijection as well, because one-to-one correspondence. So if we assume that T is uncountable, then the pre-image of T under that function, which we call X, is also uncountable because it's a one-to-one correspondence. Right, so that's, we're assuming that contradiction if that's uncountable, and then that must mean that X is uncountable. So we can say something like next, order the elements in X, which the pre-image has everything in T has exactly one pre-image, right? No two things are not good. Again, this is a bijection. And next, in increasing. So we're ordering the elements in the X in increasing order. And we can do that because X has a smallest element, right? This was one of the previous theorems. So X has the smallest element. So if we remove that, then there's another smallest element. If we remove that, there's another smallest element. So we can always do that, and we can order the elements in X. Does that make sense? What was that theorem called, by the way? It has a name. So any subset of the natural numbers has a smallest element. I forget the name of the theorem. So I think that we can order X in a sequence, basically. So let me do this in a little bit more rigorous manner. So I think it's the well-ordering property of the naturals. Yeah, well-ordering property of the naturals. So by the well-ordering property of N naturals, and since X is a subset of the naturals, X has a smallest element. So I'm gonna say X equals to X1. This is just for notation. I just introduced this notation, and you'll see why in a moment. So this is for notation. I'm going to say X is equal to X1. And that smallest element inside of X1, I'll say A1. So A1 is the smallest element in this one. Next, let X2 equal X1 set difference A1. Then again, by the well-ordering property, X2 has the smallest element. Then again, x2 has a smallest element. Say A2. Okay. So then, next let's x3 equal x2 set difference A2. And then the same thing holds for x3. x3 is the smallest element. Call that A3. So we're going to continue this process. Okay. Continue this process and build a sequence so continue this process for each element in the subsequent new sets that we make. So we continue this process and build a sequence A1, comma, A2, comma, A3, comma, dot, dot, dot. This, if we're able to write the elements in a set in a sequence, then that means that set is definitely denumerable. So you can say, hence, the original set X, which every element in here belongs to the original set X, so hence X is denumerable. A contradiction since we assume that T was uncountable, so we look at the preimage of T under our bijection, plot on X. If T was uncountable, then X was uncountable. There's a one-to-one correspondence between these two sets. But X is just a subset of the naturals. So X satisfies this well-ordering property, meaning that X has the smallest element. We can take that, make it A1, and then remove it from the set, we have a new set. Again, that new set is a subset of the naturals. So it satisfies the well-ordering property. It has a smallest element, we call it A2. We remove A2, we build another set. That's another subset of the naturals. So it has a smallest element, we call it A3. We continue this process forever, and we will build a sequence so that every element in the original set X is in a sequence, which means it's enumerable. So X is enumerable, but at the same time, X is uncountable. That's the contradiction. So again, this is kind of a messy proof, because I figured it out on the spot without like prepping or thinking about it before. But at least you got to see how when I encounter a new problem, how I think about it. Okay? So I encourage you to take this idea and fill in the details, because this is far from being a good proof. This is just an idea, a sketch, but at least I understand the idea. Once you have that, it's about filling in the details. So let me just reiterate the idea. We assume that S and T are both not finite, since otherwise the claim is done. So we assume that S is denumerable, so it's infinite and countable. And then because it's enumerable, we know there's a bijection from the naturals to the set S. And we also, since there's a bijection, we know there's an inverse from S back to the naturals. So then we assume that T is uncountable. So then X must So if T is uncountable, then the pre-image of T under that bijection, X must also be uncountable. Well-ordering property again, that's that X is a subset of naturals. So X has a smallest element. We call it A1. We remove it. The resulting set is a subset of naturals. It has a smallest element. We call it A2. Remove it. Continue this process and build a sequence. This sequence enumerates every element of X, which means that X is enumerable, which is a contradiction since if T was uncountable, X must be uncountable as well. That's the idea. Okay, so I'm kind of happy that I didn't prep on this one at all because, again, you got to see me pick and poke, think, pause, try ideas. I drew pictures to help me kind of understand. This is what you're going to build in this course, this notion of rigorous thinking and problem solving. Okay? So, let's move on. Okay. So